Predictions are that around 2030, between 4 and 5% of the world energy production is going to be spent in data centers. And at the same time, there's another crisis with data center cooling, and that is that it also uses a lot of water. But it used to be that it cost as much energy to move the cooling air as was used to process the data. It's actually the empty space, and to a lot of people that is strange. But you have to defend your empty space. For myself as an engineer, I believe very much in looking a little bit further to see that you also keep that planet intact.
Ladies and gentlemen, welcome here at Realize Live in Amsterdam 2025. I'm very excited to have a very special guest today. Wendy, welcome to the show.
Thank you.
You are actually a Thermi Award winner 2024, and not just any Thermi Award winner, but the first woman to ever win the award, right?
That's true. In 2024, I was the first female recipient of the Thermi Award, and the Thermi Award is an industry award for significant contributions to thermal management of semiconductors, so chips.
Yeah, definitely worth mentioning, Wendy. Super excited to have you on the show today. We'll talk about computational fluid dynamics, CFD, and dielectric fluids in the context of data center cooling. But before we get started, give us like a 1 or 2 sentence introduction. Who are you in the first place, Wendy? And what have you been working on in the last decade or so?
I'm Wendy Luiten, and I am a thermal engineer, and I'm also a Six Sigma Master Black Belt. And in the past 10 years, I think the most exciting thing that I did was I started my own company after a very long career at Philips Research. And wow, I can only say it's an incredible journey. And what I've been doing in the last 10 years, like research-wise, is I've been exploring at more or less the crossroads between computational fluid dynamics and also part of the Six Sigma legacy, so design space operation, exploration, and also optimization and finding the best solution for technical electronics cooling challenges.
Yeah, super exciting. You mentioned Six Sigma Master Black Belt, right? Why is it so important in the context of this event, Realize Live, to mention this?
Well, what you see in this Realize Live is a huge focus on artificial intelligence and also on workflow, on tool change, on multidisciplinary teams working on a big topic. And this whole point about the tool chains and the exploration of the design space is something that's also well known from the Design for Six Sigma way of working. And it's exciting to see how something that was very difficult to do actually in the past is now becoming much more accessible to non-statistical experts, so to speak.
Yeah, absolutely. We mentioned data center cooling a couple of seconds ago. Why is that kind of, let's have a look maybe at the status quo of data center cooling, right? Why is it becoming a crisis, if it's even a crisis right now, maybe in the future, even in the context of AI? Why is data center cooling much more important or becoming more important in the next couple of years or decades?
Well, what you see is that AI is definitely feeling a need, but an AI answer to a question uses more energy. So when you ask Google a question, it used to be you got an answer. Now you get an AI answer together with it, but that AI answer costs like 10 times as much energy to make. And what you see is that means that there's going to be a huge growth in data centers and also a huge growth in energy consumption. Predictions are that around 2030, between 4 and 5% of the world energy production is going to be spent in data centers. Apart from the environmental aspects, there's also a technical aspect here, because all that energy is converted into heat. And at the same time, the IT equipment in the data center is susceptible to heat. So you get problems with performance and lifetime if the stuff gets too hot. At this moment in time, conventional cooling is with air. And moving the air itself also costs tremendous amounts of energy. It used to be, but it's better now, but it used to be that it costs as much energy to move the cooling air as was used to process the data. So that's that doesn't look that well. So you want to have something that is more energy efficient. And at the same time, there's another crisis with data center cooling, and that is that it also uses a lot of water. And there are many parts of the earth where drinking water, so clean drinking water, is a premium thing. So to spend all that in a data center, if you can avoid it, it's obvious that you want to avoid it.
Absolutely. This is exactly where it comes to CFD, right? Computational fluid dynamics. So how can we use computational methods and mathematics and engineering actually at the end of the day to optimize the cooling system of data centers?
Well, what I did is I did the calculations. So I compared cooling with air to cooling with liquids. Liquids can contain much more heat compared to air. So liquid cooling is, I would say, the next step and already ongoing in data center cooling. But also for liquid cooling, there are different possibilities to go about it. You can cool an individual chip, but with a little block and tubes. But if you have multiple chips, you end up with an awful lot of blocks and tubes. So the next step after that is a method that is called immersion cooling. So basically you have like a tank of fluid and you just drop the board into it. And then the entire board is in contact with this cooling fluid and can cool. Of course, you cannot do that with any liquid. You need to do that with liquid that is electrically non-conductive. Because if not, then poof, says the board, and you're done for it. And of course, you can then use computational fluid dynamics to calculate what is the best option and also how far can you go, because there are always lots of trade-offs to be made.
Why do you think physical testing is so important, even though we have computational fluid dynamics? So we need actually both at the end of the day, but why do you think CFD plays such an important role in, for example, simulating data centers?
I think the beauty of CFD is that you can, you never calculate one case. You calculate hundreds of cases. And from these hundreds of cases, you can look at the trade-offs and then select the one that has the best trade-off between cooling and size and, in this case, also environmental impact. And if you do it with hardware testing, that's something that you absolutely need to do. But you typically don't want to do figuring out what are the best options using hardware, because you need to make all that hardware. And that's expensive and takes a lot of time. And I don't think you will easily make like 100 or 200 prototypes to find which is the best one. And with computational fluid dynamics, that's something that I routinely do.
Yeah. When we talk about the setup, let's go a little bit nerdy for a couple of minutes here. The setup in CFD, the boundary conditions, the setup, the geometry, etc. What is important to understand or note when doing these data center cooling simulations in CFD?
I think basically the most important thing is to have a good representation of what could be an actual case. And for this, I actually use the information of the Open Computing Group. So that's an open source of information of people that work in the industry and that have sat together and said, this is more or less what we expect from an immersion cooling setup.
When we talk about the key metrics that you're evaluating during CFD studies for data centers, what are the key parameters that you're looking at?
From the technical point of view, the key parameter that I looked at is how hot is the chip, depending on how much energy the board is using, because these boards are also going up in dissipation. For the study that I did, I used a board that was introduced in the spring of 2024 by NVIDIA, and that has a top dissipation of 2000 watts. So that's a lot of watts. And then 8 of them into an immersion tank and see how that is doing with liquid cooling.
Got it. I would be very interested, Wendy, in the setup of the boundary conditions in the CFD setup. So how do you actually define the parameters? Where do you get them from? And how do you actually do the parameter study inside of the CFD simulation?
Okay, well, I usually look at a relevant case. So in this case, I took the tank from information that I found on the internet on suppliers of immersion tanks. I took the server board that I calculated from I got the geometry from pictures of that NVIDIA board. And as for the properties of the liquids, I looked at the data sheets of the suppliers of these liquids. And then looking at what type of use conditions, also the Open Computing group has some resources on that. And also, of course, I have a lot of industry experience. So I know from my work that it's always the temperature of the IC, but you cannot, because you do not make the IC, you cannot specify something with the junction because what's inside the IC is not in your control. So to overcome that, I said, I'm going to look at an average surface temperature of the IC on this board, and I'm going to put in commercially available liquids and use a pump that's also a commercially available pump, derated for the viscosity, and also a tank like what I see in supplier information.
I see. Okay, very interesting. I'm wondering, Wendy, just a question that popped into my mind is, of course, if you optimize for performance, there's the trade-off between performance and sustainability, that aspect.
Yes.
So how do you actually balance those two, if it's only two parameters that we're looking at right now?
Yes, well, first of all, I think with performance, we have to look also a little bit at the use cases. You have operational performance, so that is when everything goes well. But of course, for a data center, you also need to have 24/7 availability. So you have an absolute need for stuff like concurrent repair and maintenance. You cannot have, if you are going to upgrade the board, that you kind of shut down the data center. This will not go over well. So the thing needs to be running, and you need to be able to take out the board and put back another board. So that's just a different use case that's very important. And then there's also, you need to make sure, also because of the 24/7 running, that if you have a failure in a pump, for instance, that the thing still keeps on running while people are busy to repair that pump. So there are different use cases that I have been using, and performance-wise, there's I would say one parameter that I looked at, and that is that the IC surface temperature cannot go above 85 degrees C because you have memories on that IC. And I also took the inlet temperature of the fluid at 40 degrees C because at that temperature it's possible to use that heat also for stuff like heating greenhouses or heating domestic housing.
I see. Interesting. Is there like maybe a question on the side? Is there a physical limit of how much we can actually cool in terms of cooling performance? So for example, if a chip gets very, very hot and we put in more and more transistors on a specific chip, right? So more heat is being developed, physically speaking. Is there like a physical limit of how much heat we can get rid of in a system? If you understand my question.
I think I understand your question. Basically, the more heat you put in, the higher the temperature gets. But that's always a temperature difference between the temperature of the liquid that comes in and the temperature of the chip itself. So the temperature of the chip above 85, you typically get problems with performance, with memories. But if you put in more heat, you can then say, okay, I can put in more liquid to take away the heat, but what is more effective is to lower the temperature of the incoming fluid. And I would say that present-day data centers do not run at 40 degrees C inlet temperature. They run at 20, 25, more or less. So I already took a huge leap into the future, saying, I mean, last year at Summitrum, the keynote speaker of Dell expressed the amount of energy that they needed to use in terms of how many nuclear reactors. And I go like, that's an awful lot of energy to use and then discard. And that's the reason why I go like, if you do that with, if you can have the temperature a bit higher and reuse that heat for domestic heating or for greenhouses, it's a much better use of energy, huh?
Absolutely.
Because it's all taking from the planet. We only have one.
Yeah.
So it's for myself as an engineer, I believe very much in looking a little bit further to see that you also keep that planet intact.
Absolutely, yeah, I would 100% agree. I'm wondering, Wendy, when it comes to pitfalls when designing these systems from an engineering point of view, meaning like building these systems, but actually simulating these systems, do you have some pitfalls that you can mention?
Yes, definitely. I think the first pitfall is the pitfall that we have already discussed, and that is only focusing on the temperature, only focusing on the size of the pump, that type of stuff. That's the first pitfall, because the thing isn't working in isolation. You should also look at what's happening around it. And in this case, what's the environmental toll of using a certain solution? So that's one pitfall. The next pitfall, I would say, from my experience, is that a lot of people look at cooling as something like you buy a fan and you put it in and then it's solved. But a lot of the cooling is actually decided much more earlier in the beginning, in the mechanical layout, because it's also the space where you did not put anything. That's the space that is controlling how your liquid flow is. So there's nothing there, but you have to defend that empty space because that's where your liquid is going through. Yeah. And if somebody says, oh, there's nothing there, I'll put something in, then your whole cooling design is gone. So it's actually the empty space. And to a lot of people, that is strange. But you have to defend your empty space.
Yeah. Do you think, like, apart from that, do you think there's more things people get wrong about liquid cooling or immersion cooling? Maybe some common misconceptions they have about liquid cooling?
People are very afraid always of getting leakages, but there's been a tremendous progress in making connectors that leak-free connectors, so it's tremendous improvement. And apart from that, there's also a misconception about the different types of immersion cooling that I have been looking into. Traditionally, cooling liquids, dielectric cooling liquids, because you hang that board in the tank, so the liquid cannot be electrically conductive. Traditionally, you had fluor-based liquids that were used for that, and they have been known since the 90s to be excellent solutions for that. And the misconception is that these are the best liquids. And what you see nowadays is you can also go for oils or even for plant-based oils. The misconception that many people think is that they say the fluor-based liquids are much thinner, so therefore you get much more flow and they will cool better, which is not the case because the oils are more thick, but they have a much better thermal conductivity. So in order to get the heat out, thermal conductivity high is a good thing. And I actually did all these simulations comparing the three different liquids. And I found out that thermally speaking, the difference between this fluor-based and these oils was extremely small. But in terms of the environment, fluor is an, everlasting chemical. And also is known to have potentially bad effects on the environment, on the atmosphere, on the soil, on the health of people. And if you look at alternatives like oil or plant-based oil, the plant-based oil is a renewable resource, but also when you're done with the oil, there's a specific test where they look at soil degradation. And you put the plant-based oil in the test bed, and in 8 days, the soil bacteria have eaten the plant-based oil. So in terms of environmental impact, there's a huge difference in liquids.
When people want to get started, Wendy, before we wrap it up, there's also CFD practitioners watching this video, this podcast. Maybe they're getting started with CFD, maybe they're a little bit more advanced. What would you recommend them to do? Maybe a book recommendation, a paper recommendation, or maybe a simulation tool to start with when they want to deal with liquid cooling, for example?
Good question. Looking at liquid cooling, it's actually the topic of the advanced thermal training that I give, but I'm not sure that that is something you can say on a podcast. There will also be a paper out on Therminic on different ways of analytically estimating what cooling performance you can get with different liquids. And as for books, the problem that there is with a lot of these books is that they were made for liquid cooling somewhere in the early last century. So most of the text on liquid cooling are filled with correlations that were made on tubes. I have seen the reproductions of the original graphs with the pencil on double logarithmic paper. So that's a little bit the problem with the classical text on liquid cooling. Let me put it like this. They're absolutely valuable. There's a lot of truth in there, but they were made in, say, 1920.
Yeah.
So the accuracy is like factor 2 or 3. And in the paper that I'm presenting at the next Therminic, I will more or less detail a way of working for the common engineer with Excel to figure out how that works. And thinking about a book, that's also, it's difficult for me to come up with.
It is difficult, and I think, yeah, definitely, Wendy. And the thing is, some people will always ask under the podcast, can you give us a book recommendation? But I think you put it quite well.
We are still writing the book. Actually, I am writing a book together with some other people on this exact subject, because what you see is that lots and lots of the classical text still go with engineering correlations, and they have their place, but the accuracy compared to what you want is not where it should be. So typically in the design flow, I would use those methods with an Excel spreadsheet to get a rough idea, ballpark of what is possible. And then I would pop it into CFD really very early. You can do that with Sketch, because the first data point is always the one that gives you the most information. And maybe that's a good recommendation. What I see is a lot of people wait for the CAD to be like almost finished before they go to the CFD. You don't need all the detail. You need to know what's the size of the box. You need to know more or less the mechanical layout, or how much open space there is. What are all these things dissipating, and also how hot are they allowed to be? And if you have that, you can do a design, a CFD simulation, really in the beginning, just with the box and some rough shapes, and already get a good idea. Somewhere around 2000, I was one of the thermal architects of the world's first consumer flat TV. That's how we did it. And you can imagine, this is 25 years ago. We couldn't dream of the computational resources that we have nowadays. But just getting that first data point is already very valuable. So maybe that's the recommendation. Start early with CFD and start as simple as possible.
Divide and conquer.
Probably, yeah.
Yeah, very good. I like the very detailed answer, Wendy. I have one last question. AI on this event, Realize Live 2025, is a very hot topic, no pun intended. Are you seeing use of artificial intelligence when designing data centers, for example, for CFD? Is there already some AI enhanced simulation methods?
Not that I know of, but I don't doubt that somebody is working on it.
Excellent. Thank you so much, Wendy.
Thank you.
That was another podcast episode here at Realize Live 2025 in Amsterdam. If you want to have more information about Siemens or SimCenter, make sure to follow all the links in the description. And if you want to follow and subscribe, make sure to do so, and I'll see you in the next episode.